So we are going to complete today our lesson, The Wave Nature of Light. Today we are going to talk about the light behavior through different media. According to the ability of the media to allow light to pass through, they are classified into three groups: transparent medium, opaque medium, and translucent medium. The transparent medium, it is the medium which permits the light to pass through it, or permits most of the light or all of the light to pass through it as air and pure water. But the opaque medium doesn't permit any light to pass through it as wood or metal. The translucent medium, it permits part of the light to pass through it and absorbs the rest as flint glass or frosted glass or tissue paper. So we have the transparent medium. As you see, it permits all light to pass through. The translucent medium, it allows some light to pass through, but the opaque medium, it doesn't allow any light to pass through it. But as the thickness of the transparent medium increases, its probability to allow light to pass decrease. What does that mean? It means that if the thickness of the transparent medium increase, it can't allow most of the light to pass through it as possible, because the light travels through a transparent medium in a form of straight lines. But when the thickness is controlled, if the thickness increased, the light can't pass with the same speed and with the same permeability. It can't pass with the same permeability. We can see the fish at the bottom of the river. Why? Because the thickness of the water at the bottom is large enough to prevent light to pass. So as you see in the picture, we can see the fish in the water because due to the thickness of the water, although the water is a transparent medium, but the thickness doesn't allow the light to pass through it. So we can't see the fish at the bottom of this river. Again, so by increasing the thickness of the transparent medium, the quantity of light which passes through it decreases until there is no vision, as you see in these glass sheets. By increasing the number of the glass sheets, the permeability of light to pass through it decreases until there is no vision at all. Secondly, we have to talk about the light intensity or the brightness of the electric source. It is the quantity of light which falls perpendicular on a unit area of a surface in 1 second. As you see in this picture, all the lamps are lightening, but they are lightening with different light intensity. How can we measure this light intensity? It is the quantity of light which falls perpendicular on a unit area. Unit area means 1 square meter or 1 square centimeter of a surface area in 1 second. So again, the light intensity, it is the quantity of light which falls perpendicular on a unit area of a surface in 1 second. Light intensity decreases when the distance between the surface and the light source increases. It means that when the distance increases between the surface and the light source, we find that the light intensity decreases. The brightness of the light decreases, and this can be known as the inverse square law of light. The inverse square law of light shows that the light intensity of a surface is inversely proportional with the squared distance between the surface and the source of light. And this is the same rule we have taken in the previous lesson about the sound. It was the inverse square law of sound. Again, this is the same rule but of light. It is the inverse square law of light. As you see, by increasing the distance, the light intensity decreases. By increasing the distance, the light intensity decreases. Here, the light intensity is more than these or those. So why here the light intensity decrease? Because the distance increase. So when the distance increases from 1 meter to 3 meters, we find that the light intensity decreases. Some questions: what happens if the distance between the light source and the surface is doubled? Now the light intensity will decrease to its quarter. Why? Because the light intensity is inversely proportional with the square the distance. Not the distance only, no, the square the distance. Again, another question. The distance between the light source and the surface decreased to the half. What happens if this distance decreased to its half? We find that the light intensity in this case will increase 4 times. We will go to show you a video which shows this inverse square law of light.
This lecture involves the intensity of light. That essentially the further one gets from a source, the lower the intensity. And we can apply this to both sound and light. The further I am from a sound source, the less intense it's going to be. In other words, the less volume and the lower the decibel value. In terms of light, it's going to be less bright. We can look at this using the inverse square law, that light appears less bright or less luminous the further the observer is from the light source. So on the left here, if I imagine that I have a light emitting source, I can call it a light bulb or a star. The rays coming out of the emitting source represent photons. Photons are the pure energy that we call light, traveling in straight lines, and that's why we see these arrows. As you move further from the source, the intensity of the light appears to decrease. This is called the inverse square law. As I increase the distance from the source, I decrease the luminosity by its inverse square, or the object appears less bright the further I get from it. So here's how it works. According to the inverse square law, according to the law, the power of the light will be inversely proportional to the square of the distance. Now it sounds really wordy, but think of it this way. If we take a distance of 2 and we square it, we get 4, that the inverse of which would be 1/4, or rather a quarter of the original power, not half. Therefore, light intensity is 1 over d squared. So let's look at that, because those sound a little bit messy. Let's say that I have a value at 1 meter. If I go to 2 meters, notice, if I'm 1 meter away, it has a value of, let's just say, 1. If I go twice as far, if I'm 2 meters from the light, it's going to have 1/4 the intensity it did when I'm at the 1 meter mark, right? If I'm 1 meter and I have an intensity of 1, if I go 2 meters, I'm twice as far. I'm going to have 1/4 the intensity. If I go 3 meters from the light source, I'm going to have 1/9 the light intensity. So the inverse square is simply saying that if I'm 4 meters away from the source, if I originally started off with, let's just say, 1 watt, and I'm 4 meters here, I'm only going to have 1/16. It's going to be much, much dimmer at this location. It doesn't say that the brightness changed. It simply says the way I perceive that light is what is decreasing. And it's decreasing at an inverse square. So let's do some numbers here. For the inverse square law of intensity, let's say that at 1 meter away, I have an intensity of 8 watts per meter squared. That if I am 2 meters away, right, if I think of it this way, 2 by 2 area, it's only going to have 1/4 the intensity as it was at 1 meter away. It's going to be 1/4. So 1/4 of 8 watts per meter squared is 2 watts per meter squared. So let's do the math. A light has an intensity of 10 watts from 1 meter. Okay, so I'm changing this number. 10 watts from 1 meter. What happens to the light's intensity if one is further from the source? Well, I just lectured to you that the intensity decreases by an inverse square. So what is the light's intensity at 2 meters away? Well, 2 meters is 2 times further than 1 meter, so it's going to be 1/4 of 10 watts. Therefore, 1/4 of 10, or 10 divided by 4, is 2.5 watts of intensity. So what if the light's intensity, or what is the light's intensity if one were 4 meters away? Well, 4 meters away from my reference of 1 is going to be 1/16. So 1/16 of 10 meters is going to be 0.6 watts per meter squared. And I would take my 10 watts at 1 meter and divide it by, if I'm 4 meters away, it'd be 1/16, right? Inverse square. The distance of 4 meters further